Hello dear friends. Today we will see a new topic that is called inductance. Now what is this phenomena? So actually an electric current can be induced in a coil by flux change produced by another coil in the vicinity or the flux change produced by the same coil. This phenomena is called inductance. Now in this case, when this phenomena takes place, we can say that in both of these cases, that is changing flux by another coil in the same vicinity or changing flux by the circuit itself, in all the case the change in flux or the flux is directly proportional to the current that is maybe passing through another coil or passing in the same circuit. Now if the geometry of the coil does not vary with time, that means if the shape of the coil or number of turns of the coil does not change, then we can say that this phi or the time rate of the flux, that is d phi by dt, is also proportional to di upon dt. So this is called the inductance. We can also say that whatever constant of proportionality is used, that is in this relation, is generally termed as inductance. So for suppose a closely wound coil of capital N turns and the same magnetic flux is linked with all the turns, when the flux phi b through the coil changes, each turn contributes to the inductance of induced EMF. Therefore, a term called flux linkage is used, which is equals to N phi b for the closely wound coil, and such a case that for closely wound N coils of any coil produces change in flux linkage, and that is considered that is n number of turns with flux phi b is proportional to I. Now the constant of this proportionality in this relation is called inductance. So we can say that it is denoted by generally as capital H in terms of Henry, who is the discoverer of this phenomena. We shall see that inductance depends only on the geometry of the coil and intrinsic material properties. This aspect is akin to the capacitance, which for parallel plate capacitor depends on the plate area and plate separation. So that is also the geometric condition, and the dielectric constant K of the intervening medium, which is intrinsic material property also. So in general, this phenomena or this relation, that is a change in the flux or the flux link with the coil, is directly proportional to the current it calls inductance of the given coils or the given system. Inductance is a scalar quantity, so we can say that it is a scalar quantity, and as I explained, its dimensional formula is obviously, actually it is denoted by H. So H, or sometimes it is also denoted by M. So H or M, it has relation. It has also term as L. So these are the different symbols for the inductance, its dimensional formula. So suppose if I say that two coils are linked with each other, say this is coil 1 and we consider another coil which is linked with it in this manner, then in this case the flux change of the one coil or the current change in a one coil also changes the flux of the other, and that is, we can say that in this case the change in a flux will relate to the current. Now the dimensional formula of it is, suppose right now we consider that this constant is small k, just for the simplicity. So we can say that this n phi b is equals to ki, and therefore this k is equals to n phi b over I. So then we will use different symbols for the inductance at the condition belongs to whether it is due to another coil or it is in the same circuit. So on the basis of that, first we derive the dimensional formula. So the dimensional formula is due to flux upon current. So it is given by M1 L2 T minus 2 A minus 2. So it is easy to derive. We can say that flux has dimensional formula that we have already seen in chapter number 1 also, that is M1 L2 T minus 1 A minus 1, and we know that, sorry, it is T minus 2 and A minus 1, and current that I has a dimensional formula that is A1. So here when we derive, we can say that we consider here the phenomena, that is, the equation is simply given by that we can derive. Suppose this k is here, so it is M1 L2 T minus 2 A minus 1 over A, and that is M1 L2 T minus 2 A minus 2. So this is the dimensional formula of inductance, and the SI unit of inductance is either Henry in the name of the scientist. Hello dear friends, now we will see a new condition that is called mutual inductance. To understand this phenomena, we shall consider a figure that is drawn here. These two long coaxial solenoids, each of length L, are given. They are coaxial. Now we denote that the radius of the inner solenoid S1 by R1 and the number of turns per unit length by N1. So see careful that number of turns per unit length for solenoid 1, that is N1, that is number of turns per unit length, and in a same manner number of turns per unit length for second solenoid is given by N2 over L, that is small n. The corresponding quantities for the outer solenoid S2 are R2 and small n2 respectively. Now we consider that N1, capital N1 and capital N2 be the total number of turns of coils S1 and S2 respectively. Now we say that when a current I2 pass through the coil S2, it turns set up magnetic flux through S1. Let us denote it by phi 1, and the corresponding flux linkage with the solenoid S1 is given by, that is N1 phi 1 is proportional to I2. Now here in the condition, the change or the linkage of the flux is with the current of the other coil, and therefore the proportionality and the phenomena is given as a mutual inductance. So when we add a constant, we can say that N1 phi 1 is equals to M12 into I2. Here M12 is called mutual inductance of solenoid S1 with respect to solenoid S2. It is also referred to as coefficient of mutual induction. For these simple coaxial solenoids, it is possible to calculate M12. The magnetic field due to the current I2 in S2 is obviously, as per for the solenoid, we can say that magnetic field due to the solenoid is mu n I. So for coil 2 it is given by that magnetic field in coil 2 is equals to mu 0 N2 I2. Now the resulting flux linkage with coil S1, that is N1 phi 1, and that flux is equals to B into A. So here we will say that area of the coil 1, so area of the coil 1, that is number of turns in coil 1, area of coil 1, and flux link with the coil 2. So here N1 is given, that is N1 into small l, A, that is area of cross section, that is pi r1 square, and B2 that is given by mu 0 N2 I2. Now if we compare, we get mu 0 N1 N2 mu 0 N1 N2, then all the conditions, that is pi r1 square and into L into I2, so L into I2. Now we can say that all other quantities are constant except I, because as I changes, the linked flux will also change. So here we can say that N1L is the total number of turns in solenoid S1, and thus we can say that from the equation that I denote here with the term N1 phi 1 is equals to M12 I2, if we compare the same equation over here, that is N1 phi1, then the remaining part of the coil that we can compare here is given by, if we compare them together here, then I can write that M12 is equals to mu 0 N1 N2 pi R1 square into L. So this is called the mutual inductance link with these two coils. Here we have to note that we neglected the edge effects and considered the magnetic field mu 0 N2 I2 to be uniform throughout the length and width of the solenoid S2. Now this is a good approximation, keeping in mind that the solenoid is long. That means the length of the solenoid is very much greater than the radius of the solenoid R2 or R1. We now consider the reverse case, that is a current I1 passes through the solenoid S1. So in the case number 2, we can say that current I2 is passed through the solenoid S1. Current I1 is passed through the solenoid S1, and flux linkage with the S2 is given by, that is N2 phi 2 is equals to M21 I1, that is change in the flux due to I1. Here M21 is also called the mutual inductance of solenoid S2 with respect to solenoid S1. The flux due to the current I1 in S1 can be assumed as this, that is, suppose we consider this as our first equation. Now we apply the equation as per as chapter number 4 for the flux. We can say that N2 phi 2 is equals to, here we can say this is N2 A2, but magnetic field will be for the 1. So this will be N2 L pi R2 square, but here we will see one thing, that the area of the coil will be the smallest part. So here area that we will have to consider cannot have the value of A2 because it is an outer solenoid. So we can only keep the area of the smallest one. So this will also remain pi R1 square, and then mu 0 N1 I1. If we compare this equation, then we can get again, that is N2 phi 2 is equals to mu 0 N1 N2. Then our equation can be written as pi R1 square into L into I1. So here if we compare two equations above, then we can say that therefore M21 is written as equals to mu 0 N1 N2 pi R1 square into L. So here if we consider the case, suppose I give this as result 1 and I give it as a 2, I can compare and I can say that from 1 and 2 that M12 is equals to M21, that is equals to M. So we have demonstrated this equality for a long coaxial solenoids. However, the relation is far more general. Here we have to note that if the inner solenoid was much shorter than the outer solenoid, then we should still have the calculate the flux linkage with N1 because the inner solenoid is effectively immersed in a uniform magnetic field due to the outer solenoid. Now in this case, the calculation of M12 would be easy. However, it would be extremely difficult to calculate the flux link with the outer solenoid as the magnetic field due to the inner solenoid would vary across the length as well as cross section of the outer solenoid, and therefore the calculation of M21 would also be extremely difficult in that case. So the equality M12 equals to M21 is very useful in such situation. Now we explain the above example with air as medium within the solenoids instead of medium of relative permeability mu r had been present. The mutual inductance would be, in the case we can have, in that case the mutual inductance is given by, that is in a medium some other than the air, m is equals to mu r and all other terms into mu 0 n1 n2 into pi r 1 square into L. So it is also important to know that the mutual inductance of a pair of coils or solenoids etc. depends on their separation as well as their relative orientation. Now let us we consider the experiment number 6.3 and in 6.2, that is the topic related to historical experiment. We can consider one more thing as per as that flux change. So here suppose we consider that for coil 1 and coil 2, suppose we are given arrangement of say coil 1 and somewhere it is given coil 2 with galvanometer only, and we consider that the flux link with them is somehow common in some way, then we can have the current varying with time for the coil 1 is depends on the current variation in the I2. So we can simply consider that the flux N1 is equals to Mi2. So suppose this is coil 2, this is coil 1. Here we can say that if current I2 pass through it, here we consider, here suppose that number of turns in coil 1, here that is N1, and here suppose that is N2, then overall consideration can be written that if the current is varying with time, then d by dt, that is N1 is equals to d by dt Mi2, and ultimately that is d5 by dt as per as Faraday's law is giving us an EMF. So E1 is minus n d5 over dt, that is represented by the same way we can write this is equals to that minus m di2 upon dt, and therefore we can say that E1 is equals to minus of m di2 upon dt. Therefore, if we make M as a subject, we can say that is EMF per change in current is also called that mutual inductance. So this equation shows that varying current in a coil can induce EMF in the neighboring coil, and the magnitude of the induced EMF depends upon the rate of change of current and mutual inductance of the two coils.